Alright, I'm back, and right now I'm going to show you what we do when we don't know the population standard deviation. So let's move down a page, give ourselves a couple more pages of space. Okay, so we found the confidence interval when sigma x was known. I'm going to show you, before we go further, I'm going to show you what the formula looks like for when we don't know the standard deviation of the population. What we do is we use the sample standard deviation to estimate the population standard deviation. So, what does this look like? Well, it gives us this formula. I'm just going to show it to you now, and we're going to walk through it, and then I'll talk about it, and then I'll show it to you again. You have the one right there. Well, this is just very slightly different. T alpha over 2 s over the square root of n. Okay, so the differences are, well, 1, we have s instead of sigma, and 2, instead of z, we're using t. Those are the differences, right, between this and this. They're very similar. Okay, so what's still true? Well, we still know that this is the sampling distribution of x bar. Right? We still know that the sampling distribution of x bar is centered at mu x, and it has this standard deviation, mu x over square root of n. The problem is we don't know what this is, right? And we don't know what this is. So what we do is we use this to estimate it. The problem, what that does is it introduces some more error. We're going to take our sample standard deviation. We're going to use that to estimate the population standard deviation. It is going to be wrong. That's okay. You know, we're often wrong. Everybody's wrong about everything, more or less. The problem is not being wrong. There's nothing wrong with being wrong. The problem is how do we take advantage of the way in which we are wrong to be responsible with it. Okay, so because s does not equal sigma x, we need to account for it. Okay, so what is s? Let's talk about that real quick just to get an idea. If you recall, s, which is the sample standard deviation, is a formula that you learned in previous statistics classes, reviewed it for this class, presumably. And you can figure it out as the square root of s squared, which is not all that helpful, or the square root of the sum from I equals 1 to n of x sub I minus x bar, the quantity squared, all over n minus 1. Well, what the heck is this? Well, let's break it down just a little bit. X bar is the sample mean. Okay, that means xi minus x bar is individualized deviation from the sample mean. So if the average height is 54 inches and you're 57 inches, then you deviate from your 3 inches deviant. And that's the way to think of it. Somebody who's shorter would also be 3 inches deviant. Right? People deviate from the mean, and this is a measure of each person's deviation. We take that and then we square it for each person, which has the effect of making them all positive. So when we add them together, they add up instead of canceling each other out. It also has the effect of overweighting outliers, because if you're off by 1 inch, well, that squared is 1. 2 inches squared is 4. 3 inches squared is 9. Those aren't so big. But if you're off by 7 inches, well, now that's 49. Or if you're off by 10 inches, that's 100. So that counts a lot. But so this is each individual squared deviation from the mean. We add them together, and then we divide them by something that's close to the sample size. So you can think of this as kind of a measure of the average deviation from the mean. That's roughly what it is. That's what we're using it to account for. Now it's a guess as to the population. We can use this to estimate our population standard deviation, but we're going to be wrong. What that means is that instead of being able to use the standard normal distribution, we're going to have to approximate it, right, in a way that allows us to account for the additional error from estimating the shape. What we do is we use the t distribution to estimate it. So what is the t distribution? I've looked at this a little bit. Maybe not. You should have a t-table. And I'll tell you a little bit about t-distributions as we start, before we move on to that though. Alright, I'm going to pull up, let's see, I think, yeah, I have my notes, so I might as well just show them to you here so you can see them. So the t-distribution is invented, or discovered, I guess, by a guy who wrote anonymously. It has some characteristics worth noting. It's an approximation of the normal distribution in a lot of cases. It's a family of distributions. So it's a family of curves. They're indexed by numbers. So they're indexed by what's called degrees of freedom. So there's 1 degree of freedom, 2 degrees of freedom, 3 degrees of freedom, etc., all the way up to about 100. When you get over 100, you can use the standard normal. That's fine. What else? Well, it has some properties that are nice. It's symmetric, just like standard normal. The total area is 1. It's centered at 0, which is the mean, the median, and the mode. And so it has a lot in common with the standard normal distribution. We use it in similar cases. And this is what it looks like. You need to know which distribution, or how many degrees of freedom you have, in order to know which distribution you're looking at. There's the t-distribution with different degrees of freedom. So with 1 degree of freedom, we're looking at the one that's on the inside here, the middlemost. Right, this one's with 1 degree of freedom. If you have 2 degrees of freedom, it's this one. 3 degrees of freedom is, or 5 is this. All the way up to 30 is here. And the thing worth noting is actually not just in the peak, but also in the tail. 1 degree of freedom has a really fat tail. Down to 30 degrees of freedom is a really skinny tail. And the fatness of the tail is a measure of how much dispersion there is, right? What the probability is that you're going to get a weird result. So the more degrees of freedom you have, the less weird results you get. Okay, does that make sense? All right, let's pull out a t-table for you guys to look at. Let me see if I can pull mine up. The t-table tells us some stuff. Yeah, let me talk a little bit about the z-distribution first. This is not the t-table I want. It's okay. I'll find it. So when we were talking about confidence intervals, one of the things we were talking about was just how weird we have a weird z, right? So if we have an outlier, or we have a sample mean, and it's kind of almost an outlier, what that means is that on a curve, this is the sample, or this is the population mean, and our x bar is right here on the edge. Right? Now, when we normalize this using a standard normal curve, what that means is that we're going to have something like this. If it's a 95% confidence interval, that means is that we're going to relate it to the standard normal curve like so. This area here is going to be 0.95. This area here is going to be 0.475, which means that the area in the tail up here is 0.025. That's half minus half of our confidence level. And that's going to give us a certain value of z. Right? That's a weird z. A weird z here is going to be, well, you look it up on your table, you look up 0.475, and you'll find that a weird z is 1.96. That's a high-end z. Anything beyond that, any sample mean with a z-score higher than that is going to be really weird. Well, now, what we can do the same thing with t, right? What we do is we say, okay, well, here's our sample distribution, or sampling distribution, sorry, not sampling distribution. Here's our population mean, here's our x bar. We don't actually know what the standard deviation is here, right? So we can't relate it to standard normal. What we can say is, okay, we're going to approximate it with a t-distribution. The way we do this is we use n-1 degrees of freedom. And then that's our curve. That's our t-curve. So we want to know what a 95% confidence interval is. And we have 0.95 mass in here. Gives us 0.475 here. 0.025 is still the amount that we think is there. Now we're going to relate it to our t-distribution. So we draw a t-distribution. We label it with the degrees of freedom. And let's say we did a sample with size 27. We asked 27 people, okay? So if the degrees of freedom is equal to n-1, we're going to have 26 degrees of freedom. and that tells us which particular t curve we're looking at, right? Now it's centered at 0. We want to know what's the value of t right here that has, oh man, my straight lines are rough, 0.475 here and 0.025 here. That's what we're asking, right? Well, we can use a t-table to tell us that. T-table contains a lot less information. It actually contains, the standard normal distribution contained a lot of information about one curve, and this contains, 6 points of information about 100 different curves. 1 through 52 on the front, and all the way up to infinity on the back. I'm not going to show them all. But what matters right now is what we're looking for. So we have 26 degrees of freedom. Well, that tells us which row we should be looking at. Because in the table here, each row corresponds to one t-distribution. If we have 26 degrees of freedom, that means we're looking at this right here. That's the 26th row, right? The row with 26 degrees of freedom. And what the columns tell us is how much area is in the upper tail. You can see in this picture here, it's talking about the upper tail here. So when we go back to our picture, you can see, oh, we have 0.025 in the upper tail. And this tells us which t value will give us that. So we're in the 26 degrees of freedom curve. We're going to 0.025 in the upper tail. So 2.056 is a t that's weird there. Okay, so where's my pen again? There we go. 2.056. Now you can see that it was 1.96 in the z curve. Now it's 2.056, so we're capturing a little bit more, right? Our margin of error is going to be a little bit bigger because that number is a little bit bigger, and that's accounting for the problem that we ran into before with the fact that we don't know the population standard deviation. So the way that we can set this up is, well, we have a t right here, right, which is equal to x bar minus mu x over s divided by the square root of n. And if we multiply both sides, we do our formulas, our algebra. Multiply both sides by s over the square root of n. That will cancel these out. We subtract x bar from each side. That will cancel these out. And we will get a negative mu x equals s over the square root of n times t minus x bar. Switch that around, you get mu x equals x bar minus t alpha over 2 times s over the square root of n. That should look familiar. That's the formula we had up top. And you can add, if you work through it with another one, right on the other end, then you'll get mu 2 equals x bar plus t alpha over 2 times s over the square root of n. That's where the formula comes from. Essentially, we're just using a t-distribution instead of a z-distribution because we don't know the population standard deviation. Now, standard deviations can be a little bit confusing, so before we go any further, and just to round this out, I'll probably post some practice problem answers, but you can use the formula in practice, looking stuff up. So, what I was going to say, yes, that's right. There are 3 distributions we care about. 3 distributions. One is the population distribution. Let me hide this ribbon for now. So, one is the population distribution of x. This is how height, weight, IQ, whatever, are distributed in the population. So we have x, and it can look like a lot of crazy things. It could look like that, it could look like this, it could look like this if it's like income, it can be uniform if it's random number generator. It can look like all of those things, but it's going to have a mean, mu x, and it's going to have a standard deviation, sigma x. These are the standard deviation and mean of the population value of x, right? The population. The third one we care about is the one we can actually see. So we have the sample distribution of x. This, oftentimes we draw this with like a histogram or a bar chart. And this looks like this, right? You've got some people who are really low in your group. This is a size of n equals 20 or whatever, right? You got some people, nobody in the middle maybe you got somebody up here. This is just, how many people have each of these heights, right? This is the number of people who fall between 5'2" and 5'4". This is 5'4" and 5'6". This down here is 5'6" and 5'8". Whatever. Each of those bins, each of those bars has a certain category, and this has a mean, and it has a sample standard deviation. But last but not least, the thing we care about is the sampling distribution of X bar. And that's different, more important, and more useful in important ways. And that looks like this. It's always normally distributed. And the mean here is mu x bar, which happens to be equal to mu x, and sigma x bar, which happens to be equal to sigma x over the square root of n. Okay. And this right here, this is important, but we can't see it. This down here, this is visible. We can see it. And this is useful. I use the word analytically tractable. Math works well with this stuff when we talk about sampling distributions. So the way that the t-distribution works essentially is that if we don't know this, we use this to estimate this, and then we use that estimate to get a good guess here. This is close to s over square root of n. Problem is, if it's not so close, we can't use standard normal. We have to use the t-distribution. We fatten the tails a little bit, and that corrects for some of the problems we have. But just being able to think about the fact that there are three of these, there's a population distribution of x, there's a sampling distribution of x bar, and there's a sample distribution of x, can make this a little bit simpler. Most of the stuff we're working with is theoretical results from the sampling distribution. So we use this stuff to get our numbers, we use this stuff to get our relationships, and then we use that to infer things about this. Because that's what we really care about, is population distribution. All right, I'm over time. Hope you guys are doing well, and yep, more later. Thanks, bye.